Assalamualaikum warahmatullahi wabarakatuh. We're looking at the continuation of question 6, in which the same motor is now connected, or we can say that eventually became differentially compounded with R adjusted 175 ohms. Okay, so now what is the no load speed of the motor? Still, we are given um, this magnetization curve, which actually plot um, the shunt field current IF against shunt field current IF and actually versus EA versus IF. Okay, so basically, this magnetization curve is plotted at speed 1800 RPM. So this would be our reference speed, okay, to actually calculate the no load speed for the motor. Okay, so right now we know that it is now differentially compounded, and from this loop around here, okay, we know that EA is actually VT minus IA RA plus RS. Okay, and um, and at no load speed, obviously we're looking at IA equals to 0, so therefore EA will be equal to VT at this point, which is supposed to be 240 volts. Okay, so to use this magnetization curve, we have to basically find what is the field current when the motor is running at no load speed. Okay, so the field current is actually VT divided by R adjusted plus RF. Okay, so VT is 240 divided by 75 ohms, which is the field resistor, and then plus R adjusted 175, which will give you 240 over 250. Okay, which is you get 0.96 ampere. All right, so if you're looking at the magnetization curve, if it is probably use different color here, 0.96, which is very close to 1, right, and you go further up, you'll be looking about closely to 246, for example. Okay, so 246 volts. Okay, so if the motor is running at 1800 RPM with IF equals to 0.96, we'll be getting EA equals to 264. 246 volts. Okay, but obviously the voltage that, or the EA that we are having now is 240 volts. All right, so therefore the amount of the speed obviously will be running at a different one than the one plotted here lah. Okay, so how to do it is basically we're using the same ratio of internal generated voltage in which we have done before, which is EA2 or EA1 over N1 equals to EA2 over N2. Okay, so to get N2, or the ones that we're trying to find, so we have to calculate EA2 over EA1 times N1. Okay, so EA1 and N1 is actually your reference. All right, so your reference, basically this reference is where you get from your magnetization curve. Okay, so since this magnetization curve is actually plotted at 1000 RPM, so obviously this will be your N1. And then EA1 is this one. Okay, we know that you get EA1. So at this point, we're using this because we are considering that with IF, both of the cases is when IF is equal to 0.96, which means the the state of the flux in the machine are the same. Okay, so you have 246 volts here, and then EA at the point of no load is actually 240 volts. Okay, so we will get 1756 RPM. Okay, so this will be the no load speed. Okay, what is the speed of the motor when the armature current reaches 20 ampere? Okay, so when IA is actually 20 amps, so now EA will be much less from EA at no load. And we are following this equation because we look at this circuit at the top here, in which this line to this line is actually VT, and you have RA plus RS here, right? So that's why the equation is like this. So EA when IA is 20 ampere or is driving a load is 240 volts minus 20 RA plus RA is 0.119, RS is 0.02, 0.09 and 0.02. Oops, sorry, 0.19, 0.02. So the answer is 235.8 volts. Okay, so this is the induced voltage when the current is actually 20 ampere. So when the armature current reaches 20 ampere, we are actually looking at the field current that are actually different from the ones that we have without when it is no load, because when it is no load, this IA actually running inside the circuit, armature circuit, right? So when there is no load, obviously there is no IA, but when there is load, and when they are driving a load, then obviously we have to consider the effect of armature current into the series winding, which in the case of differentially compounded, of course, we will have much lesser effective field current. So remember that the effective field current of a compounded DC motor is actually IF. In the case of differentially compounded, is minus NSE over NF times IE, and minus armature reaction over NF. And we know from the very beginning that we are actually excluding the armature reaction in this machine. So this actually goes to 0. And you see that the effective field current, or the reduction of field current in differentially compounded DC motor actually happens when you start loading the motor, in which IA is there, okay, which flows through the winding of the armature. Okay, so your IF is 0.96 obviously, and the series turns 14, and NF is 2700. Then IA is 20. Okay, so we check back 14 and 2700. So the effective field current is 0.856 ampere. Okay, so therefore in the magnetization curve, the EA, or the reference will be the different reference now lah, because the magnetic flux or the magnetomotive force inside the machine are now reduced because of the load, or because of the current that actually flows into the armature circuit. Okay, so if we take a look back at the magnetization curve, and we want to take a look at 0.856. Okay, so 0.85 is somewhere here in the middle. So we're looking at closely to 230. So basically the new reference would be for IF equals to 0.856, then you get EA 230 at N equals to 1800 RPM. Okay, so here therefore when we are looking at the ratio, and we're computing for the speed when this happens. Okay, when the armature current reaches 20 ampere, then obviously we're looking at EA2 over EA1 times N1, which is the effect, the induced voltage is reduced to 235.8, and the reference is at 230. Okay, and the speed is 1800 rpm. So you will get value of 1845 rpm. Okay, and you can see that the speed at no load, all right, is actually 1756. Okay, at the motor. And when the current, when you are trying to drive the load with the differentially compounded motor, the speed actually increases instead of decreases. This is because, like, in a differentially compounded DC motor, the shunt magnetomotive force, which is supplied by the field circuit here, is and series magnetomotive force, which are in series with the armature circuit, actually subtract from each other. So this means that as the load on the motor increases, the armature current will increase, obviously, and the flux, because of this subtraction, will decrease. Okay, but we know that as the flux decreases, okay, the speed of the motor will increase. Okay, so this speed increase causes another increase in the load, which further increase the armature current, which eventually further decreasing the flux. Okay, and therefore the speed will keep on increasing. So if we take a look back at the theory, we will see that the torque versus speed curve is actually like this. Okay, so the torque speed characteristic, you will see that this differentially compounded motor is basically very unstable as the load is increasing, and therefore it tends to run away. Okay, so this instability is much worse than that of a shunt motor with armature reaction. So and therefore it is usually not used for any application with, it's not intentionally used for any application. Okay, and we can see that also it is impossible to start such a motor, because at starting conditions, we know that since this is subtracted here, and in the very beginning IA is very high, and since the series flux subtract, so the series field can actually reverse the magnetic polarity of the machine pole. So the motor will either typically remain still or slowly turn in the wrong direction while burning up. Okay, because of the excessive armature current. So if we actually happens to come close to this machine, when it is going to be started, the series field must be short circuited so that it behaves as ordinary shunt motor during the starting period. Okay, so I've explained to you all the different types of DC motors speed control, as well as how to analyze the circuit when we're trying to size the motor up with applications. All right. Okay, so as we move forward, we will take a look at the different types of AC motors, and how to actually size up, how to analyze the machines, as well as eventually size up the motor according to applications.